Welcome on our last lecture in today's Code Dive conference. I'm very happy to greet on the stage Radek, who's only 20 years old and he's working student at Nokia, and he's already the speaker at the Code Dive conference. It's very nice to host you today. So Radosław Szewczyk is computer science student at the Silesian University of Technology. He's interested in ML, especially in NLP. Likes building models from scratch. Avid C++ user and Python enthusiast. I'm sorry, I'm tired already. Okay, Radosław, the stage is yours. I'm very happy to meet you today.
Okay, thank you very much for a warm introduction. And today I would like to talk about NLP with the side of C++ and Python bindings. I will talk a bit about statistical basics of Naïve Bayes algorithm and how I have used PyBind 11 to speed up my project, and what are strengths and weaknesses of few options that we will analyze today. But before we start, let's talk about an elephant in the room. NLP is a subfield of artificial intelligence, and AI is everywhere right now. We have AI toasters, vacuum cleaners, toothbrushes, beehives, perfumes, everything. That's what sells nowadays, right? But in this talk, I will focus on something else. I will focus on creating your own model, not the ChatGPT wrapper. We will go down to basics at what follows. We have to manage expectations a bit. I won't show you how to build LLM and how to get OpenAI out of business, but how to build a pretty useful tool with C++ and Python. So, NLP, natural language processing, as I said earlier, is a specialized subfield within artificial intelligence and machine learning that focuses on enabling machines to understand, interpret, process, and generate human languages by bridging the gap between human communication and computer interpretation. NLP allows machine to derive meaning from natural language inputs, such as text or speech. The core of NLP lies in combination of computational linguists, which involve rule-based modeling of human language, and statistical, as well as machine learning techniques. Computational linguists. Oh. Is it okay now? Okay. So the core of NLP lies in a combination of computational linguists, which involves rule-based modeling of human language and statistical, as well as machine learning techniques. Computational linguists leverage the experience of language specialists to define language structure, syntax, semantics, and context. When combined with data-driven models and algorithms, this approach equips machine with the ability to process a vast amount of natural language data, recognize patterns, extract insights, and respond accordingly. NLP powers a wide range of applications, including machine translation, text summarization, sentiment analysis, speed recognition, and much, much more. Today, we'll be focusing on creating Naïve Bayes algorithm. This is a classification algorithm, which is type of predictive modeling technique in machine learning that aims to categorize or to classify data into predefined labels. It is one of the fundamental aspects of supervised learning, where the goal is to learn from labeled training data and use that knowledge to make predictions or to assign labels to new unseen data. Here's how it works. We will feed our program sets of two things, text and the tag. Tag will be sentiment of a given sentence, so whether a sentence is positive or negative. We could also neutral tag, but it would increase our program's complexity. And as you can see, the formula is pretty simple, but let's take a look at the example. So, given the data set of green dots and red dots, so this is our training data, we get a new data point, this uncolored dot in the circle. And now, using the Naïve Bayes theorem, we have to decide whether the data point belongs to greens or to the reds. A prior probability represents the initial assessment of probability of an event before any additional evidence or data is taken into account. It reflects probability based on previous knowledge, experiences, or assumptions before analyzing new data. Let's suppose you want to determine the probability that randomly selected person is a doctor. If you know from past data that 5% of populations are doctors, your prior probability of selecting doctor is 5%. This is your baseline estimate before considering any new information. The prior probability serves as a starting point for updating beliefs when new evidence is introduced. A posteriori probability is the revised probability of an event when new data is introduced or is taken into account. It represents the probability of, and is calculated using our Bayes theorem. So, as you can see, it is not complicated. It's pretty straightforward. But why do we need our speedy C++ combined with Python? Why can we only use C++ or Python? So, text processing and tokenizations. Those are fundamental steps in NLP as they help us transform raw data into a format suitable for analysis by filtering out elements that could blur or hinder our results. These unnecessary things typically include non-alphabetical symbols like commas, dots, slashes, exclamation marks, etc., that do not carry meaning in context of model training. In addition to these symbols, numbers may also be removed, but it depends on a specific task. However, one of the most important words to filter out are stop words. Those are common words in a given language, such as a, with, from, at, in, or are, which appear frequently, but usually carry very little information value on their own. By focusing on filtering these elements, we allow our model to capture the words as structures that truly contribute to understanding and prediction. This is where NLP programmers greatly benefit from collaboration with language experts. Our models would become nonsensical without their deep understanding of language nuance and context. It is also important to mention that models trained on English data and with English stop words, etc., are not capable of classifying or processing other languages. Tokenization defines how words are split and affects the overall comprehension of the text by the model. This is a process when we split our text into smaller units, like words or subwords called tokens. Improper tokenization can lead to misleading or irrelevant interpretations, emphasizing why this step is so critical. That's where C++ and Python bindings come into play, in these performance-critical areas. But let's start with the question, why even use Python? Why can't we only use C++? And the reasons are kind of obvious. As the Stack Overflow developer survey suggests, Python is a widely popular language. However, take it with a grain of salt. I bet results will be drastically different if we poll this audience. JavaScript wouldn't be first. Python is also simple and quick to code with very low boilerplate and supports tons and tons of libraries. Very powerful and simple to use libraries that are used by millions of professionals across dozens of different fields. So, let's get down to business. Let's merge the two and get the best out of the both worlds. What do we get? First and foremost, we get a lot of speed, especially complex operations when Python lags and C++ excels. As seen on the right-hand side of the slide, a lot of libraries take advantage of set C++ speed, performing mathematical calculations, data processing, or image processing. Secondly, we get to reuse code already written in C++ and use it in a new way, in a new context, without writing everything in Python again. We have a lot of libraries that accomplish the same thing, and here are some of the more popular ones. But today I will focus on PyMind 11 because it is very easy to use and easy to learn. So let me show you how easy it is to start using PyMind 11. We have our hello world function in C++, but we have some new code here. PyMind 11 macro that creates a module named hello module and exposes my function to Python. So what happened here? How C++ can be loaded to Python? How .so file compiled in C++ can be loaded to Python? The answer is CPython. CPython is the implementation of Python language. It is a C program that interprets Python's instructions. It works something like that. In CPython, every object, regardless of its type, is represented by a PyObject. So int, string, function, whatever. It's all represented by PyObjects. The structure contains essential information that all objects share, allowing the interpreter to manage them consistently. The CPython core reads your Python instructions to change its internal state, which is represented by set PyObjects. So the SO file that we have created earlier have instructions that change those PyObjects, so these internal states of CPython interpreter, in your memory. And that's about it. But let's take a look at a real-world example of implementing Naïve Bayes classificator with PyMind 11. I wanted to have a simple web app that is fast to write and good for data presentation, so I chose Dash. It is an easy-to-use Python library with plenty of features for this project. So, sorry. Let's take a look at the code and how PyMind 11 benefited this project. This is a part of PyMind 11 module macro, which exposes class data frame. The first line defines a new Python class data frame that wraps the C++ data frame and enables Python to interact with it. The std shared pointer part specifies that the data frame object should be managed using shared pointers, which helps manage memory automatically, allowing for shared ownership of data frame objects between Python and C++. M is a PyMind 11 module, defined a little bit higher, similarly as in the previous example. So this is a module where the Python class will be made available. Data frame in quotes is the name as it will appear in Python. So let's take a look. What do we have binded there? The first one, def init, is a default constructor of class data frame. Next, we have 4 public data members, which can be read and written directly from Python. Then I have my methods with some default arguments using pyarg. And lastly, we have 2 overloaded operators. Over at the Python side, we have our data class defined and our model class. Then we have a method calls like train, processing line, and predict. And that's about it. As you can see, writing bindings in PyMind 11 is fast and simple, but still very, very powerful. I said earlier that C++ speedup will benefit data tokenization and preprocessing. So let's take a look at a few functions and benchmark them to see if there is any improvement, and if so, how big. Firstly, let's take a look at Lawrence distance algorithm. Lawrence distance is a string metric for measuring the distance between difference between two sequences. The distance between 2 words is a minimum number of single character edits, like insertion, deletion, or substitution, required to change one word into the other. It works by building a matrix when one string is represented on the horizontal axis and second one on the vertical axis. Each cell in matrix represents the cost of converting substring up to that point. The algorithm computes values iteratively by considering the minimum cost among insertion, deletion, and substitution. Ultimately, we find our results at the bottom right cell of the matrix. So, let's take a look at the results. At this point, we have all expected that PyBind11 to be faster, but for such a simple example, the difference is quite noticeable. So, yeah, but when we add C++, it doesn't look so good after that, but still, difference is very big. Okay, next, let's take a look at data processing function. It processes a single line of text, and it makes a bunch of operations. As I said earlier, it deletes, removes special characters from the line, removes stop words every time comparing it with Lavenstein distance, and implements simple autocorrect function also with Lavenstein. So just a bunch of word transformation. And the results are much closer this time around, but the difference is still there. But let me introduce you to this middle ground. I mean, it's not really middle ground, but you will see in the moment. Enter Python C API. Python C API is a set of functions, macros, and structures provided by Python implementation, so by our CPython, that allows you to interact with Python code and objects using C or C++. It enables us to write C extensions, create new built-in modules, manipulate Python objects directly from C. This is a backend of PyBind11. This is what is simplified with PyBind11 and many libraries alike. Beside that, Python C API enables us to do a lot of cool stuff, like you can embed Python interpreter with a C application using Python C API. This makes it possible to use Python as a scripting language within a larger application. So there's a lot of cool stuff to play around here, but let's come back to our bindings. Here's an example how to expose C++ function to Python using Python C API. First function acts as a bridge between Python and C for our module. It can be called from Python code and takes PyObject self and PyObject args. Args represent the tuple of arguments passed from the Python side. And inside, firstly, we parse arguments from Python. Then we call our C++ function, and then return it as a Python object. In the next function, we are defining module methods, Lavenstein methods, then our module definition, and lastly, module initialization function, pyinit Lavenstein. PyModule create in pyinit Lavenstein creates a new module object using the Lavenstein module definition, and this function is automatically called from Python when module is imported. So there's a lot of occasions to shoot yourself in the foot here, right? But is it worth it? Yes, as always. It is much faster than PyBind11, as seen on a now updated Lavenstein benchmark. So, why the difference is so big? As I said earlier, PyBind11 is built on top of Python C API. It acts as a higher level abstraction layer that simplifies the process of creating Python bindings for C++ code by using underlying functionality provided Python C API. It simplifies binding creation. As we've seen, Python C API can be very verbose and requires significant boilerplate to create extensions and handle Python objects. PyBind11 abstracts away much of this complexity by providing more C++ friendly interface that uses modern C++ features. PyBind11 also uses Python C API to perform automatic conversions between C++ and Python types, such as translating between C++ std string and Python string, or between C++ containers like vector and Python lists. As all things in life, we have to make trade-offs, then choose what works best for our problem. It all boils down to choosing the right tool for a job. If maximum performance is your goal and you want to bind Python and C++, then Python C API offers low-level control and minimal abstraction. It enables you to finely optimize interactions between C and Python, making it ideal for performance-critical tasks. In contrast, PyBind 11 strikes a balance between power and ease of use. Leveraging modern C++ features greatly simplifies creating Python bindings for C++ code. Automatic type conversions, class bindings, and exception handling make PyBind 11 easy to use, but there is performance penalty due to the higher abstraction level. However, exposing C++ libraries to Python requires extra effort, whether using Python C API or tools like PyBind 11. Directly writing in C++, of course, provides the most control and the best performance for demanding tasks, but limits us in terms of vast range of easy and ready-to-use Python libraries. Writing purely in Python, on the other hand, offers the fastest development and easiest debugging, thanks to Python dynamic typing and ridge libraries. But Python can struggle with performance, particularly in computation-heavy loops and tasks. So if you prioritize rapid development and easy maintenance with acceptable performance overhead, PyBind 11 is excellent choice, as it reduces complexity significantly compared to using Python C API directly. So the conclusion is simple. Write it all in assembly, right? But jokes aside, to make the best choice, ask yourself, what is the critical performance need of the project? And is the added development complexity justified by expected performance gains? These are the main two actors here: performance versus complexity. Thank you for your attention. If you have any questions, feel free to ask.
Do you have some questions? Yeah, okay. On the right side.
Who has a question?
Thank you for the presentation. My question is, for instance, natural language processing try to mimicate certain part of what we have knowledge of intelligence. And I would argue that we somehow tied intelligence with speed. So the fastest we can simulate intelligence actually will correlate more on our perception of intelligence. Then how do you find the usability and let's say performance trade-off, as you mentioned in your talk? What do you think is the direction that the people are following these days, or what's your opinion on which side we should invest more? Because what we see in the market, for instance, you see in company NVIDIA and many other companies, what we see is like people moving more towards speed than actual usability to a certain extent. But also I acknowledge that it's something like PyTorch that made machine learning accessible to most people. So what are your thoughts between these two lines, basically? What do you see and what you advise people to follow more?
If I think correctly, if this was you mean, NLP is a very fast and very simple way to, for example, as I said in the talk, to analyze, for example, sentiment, right? So you don't have to have like powerful, beefy NVIDIA GPU to get great performance and very good accuracy with quite simple models, because that's it. You don't have to have LLM to analyze your for example, article for sentiment, right? If that's what you mean, but you can specify maybe a bit more.
I mean, I didn't put in context with which algorithm inside of natural processing. I was just generalizing to the biggest and the ones that we use more in the market. Because, I mean, the way you mentioned between the way we want something easier to use and we also want to trade that for speed.
Yeah, but it's all about the project that you have to work for. In my case, it started with Python being like absurdly slow. I had to like wait 5 days for my file to process, and it wasn't just it's no-brainer to think about something else, because I can't process file 5 days, then have mistake and process another 5 days the same file, right? So it was just a need for that. And also, as you said, in a lot of Python libraries, if you had to write PyTorch in Python, it would be like nightmare, right? It would take 10 years to make your model, to train your model. So that's more of necessity than like a choice.
You. Do we have another question?
Hello, thank you for your talk. I have a question about, I'm just curious, what is your experience with Python, and how does it impact the way that you approach the language models that you set? Why Python? Why exactly is it better? Is it your preferable way to work with language models?
My preferred way is C++, of course. Of course. But I chose Python for this project. I mean, to write the main code in Python, let's say, because I wanted to have GUI and to present my data somehow, right? Okay. And the thought of making it C++ library and taking it a lot of time and a lot of pain that comes with it, and it wasn't worth it. So I just chose Python and make GUI in like 2 hours, right? And just be done. Right? So
all right, thank you. That answers my question. Thanks.
Questions? Okay, I guess not. So thank you, Radosław, once again.